As you rest peacefully tonight, the oceans, covering 71% of Earth's surface, are constantly moving, not just with the familiar rise and fall of tides, but with vast currents that flow like rivers through the sea. Enormous streams of water, thousands of miles long, carrying heat from equator to poles, distributing nutrients that support marine life, and influencing weather patterns across entire continents. These ocean currents, driven by wind, temperature differences, Earth's rotation, and the Moon's gravitational pull, create a global circulation system so powerful it shapes climate, enables life, and connects every ocean basin in a planetary network of moving water. Tonight, as you drift toward sleep, you'll journey through the hidden geography of ocean currents, discovering how surface winds push water across thousands of miles, how temperature and salinity differences create deep currents that flow like underwater rivers, how the Moon's gravity not only creates tides, but also influences the mixing and circulation of ocean water, and how these currents have shaped human history, marine ecosystems, and the very climate that makes Earth habitable. The Gulf Stream, perhaps the most famous ocean current, carries warm water from the Gulf of Mexico along the eastern coast of North America and across the Atlantic toward Europe, transporting more water than all the world's rivers combined, roughly 100 times the flow of the Amazon River. This massive flow of warm water moderates the climate of Western Europe, making places like London and Paris warmer than Canadian cities at the same latitude, demonstrating how ocean currents influence climate on continental scales. The Antarctic Circumpolar Current, flowing around Antarctica unimpeded by any landmass, is the largest ocean current on Earth, transporting roughly 150 times the combined flow of all rivers. This enormous current connects the Atlantic, Pacific, and Indian Oceans, playing a crucial role in global ocean circulation and in isolating Antarctica's cold waters from warmer subtropical waters to the north. Ocean currents form a connected system, sometimes called the global conveyor belt, or thermohaline circulation, a slow, deep circulation driven by differences in water temperature, thermo, and salinity, haline, that moves water throughout the world's ocean basins over timescales of centuries. Cold, salty water sinks in the North Atlantic and Southern Ocean, flows along the ocean floor toward the equator and into other ocean basins, gradually warms and rises back to the surface, and returns toward polar regions to complete the cycle. The Moon's influence on ocean currents extends beyond the familiar twice-daily tides. Tidal currents, the horizontal movement of water associated with tides, can be powerful flows in coastal areas, straits and bays, where rising and falling tides must move large volumes of water through restricted spaces. These tidal currents transport nutrients, larvae, and sediments, creating some of the ocean's most productive ecosystems, where tidal mixing brings deep nutrients to sunlit surface waters. Tidal mixing, the stirring of ocean water caused by tidal currents flowing over seafloor topography, plays a crucial role in the global ocean circulation. As tidal currents flow over underwater ridges, seamounts, and continental shelves, they create turbulence that mixes warm surface water with cold, deep water, influencing the vertical distribution of heat, nutrients, and dissolved gases throughout the ocean. Without this tidal mixing, the ocean would be more stratified, with less exchange between surface and deep waters. The interaction between currents and the Moon creates complex patterns of water movement that vary with location, depth, and time. Coastal regions experience strong tidal currents that reverse direction every 6 hours, while open ocean areas experience weaker but more persistent wind-driven currents modified by tidal influences. Near underwater features like the Hawaiian Ridge or the Mid-Atlantic Ridge, tidal currents create internal waves, waves that propagate below the surface along density boundaries between water layers that can transport energy and mix water across vast ocean areas. As you prepare to explore ocean currents tonight, rest in the knowledge that the seemingly static ocean is actually in constant motion, with every part connected to every other part through currents that flow at the surface and in the depths, driven by forces ranging from local winds to the moon's gravity to density differences created by solar heating and ice formation. These currents have carried explorers across oceans, distributed life throughout marine ecosystems, regulated Earth's climate for millions of years, and continue shaping the planet in ways both obvious and subtle. The wind-driven surface. How atmosphere moves the ocean. Journey now across the surface of the ocean, where persistent winds push water into the great surface currents that sailors have used for centuries, discovering how atmospheric circulation creates ocean circulation, how the Coriolis effect deflects moving water, and how surface currents form vast rotating gyres that dominate each ocean basin. The surface ocean, roughly the upper 1,000 feet, moves primarily in response to wind stress. When wind blows across the ocean surface, friction between moving air and water transfers energy, pushing surface water in the direction of the wind. But the water doesn't move exactly in the wind's direction. Instead, it moves at an angle to the wind, typically about 45 degrees to the right in the northern hemisphere and 45 degrees to the left in the southern hemisphere, due to the Coriolis effect created by Earth's rotation. This wind-driven surface layer, as it moves, drags on water below it through friction, creating a spiral of decreasing velocity with depth called the Ekman spiral. Each successive layer moves slower and at a greater angle to the wind direction than the layer above it. When you average the transport of all these layers together, the net movement of water is perpendicular to the wind direction, 90 degrees to the right of the wind in the northern hemisphere, 90 degrees to the left in the southern hemisphere. The trade winds, persistent easterly winds in the tropics, blow from east to west, pushing surface water westward in both hemispheres. This creates the north and south equatorial currents that flow across the Atlantic and Pacific Oceans, carrying warm tropical water toward the western boundaries of these ocean basins. When this water encounters continents, it must turn, creating the strong western boundary currents that flow poleward along continental margins. The Gulf Stream represents the North Atlantic's western boundary current, flowing northward along the eastern United States before turning eastward across the Atlantic. The Kuroshio current serves the same function in the North Pacific, flowing northward along Japan. These western boundary currents are narrow, perhaps 50 to 100 miles wide, deep, extending down 3,000 feet or more, and fast, flowing at speeds up to 5 miles per hour, remarkable for ocean currents that typically move much more slowly. The prevailing westerlies, winds blowing from west to east in temperate latitudes, drive surface water eastward across the mid-latitudes of both hemispheres. In the North Atlantic, this creates the North Atlantic Current, an extension of the Gulf Stream that carries warm water toward Europe. In the North Pacific, The North Pacific Current flows eastward toward North America. These currents are broader, shallower, and slower than western boundary currents, but they still transport enormous volumes of water and heat across ocean basins. When these eastward flowing currents reach the eastern boundaries of ocean basins, they split, with some water flowing toward the equator along continental western coasts as cold eastern boundary currents. The California Current, the Canary Current, the Peru Current, Humboldt Current, and the Benguela Current are examples of these eastern boundary flows that bring cool water from higher latitudes toward the tropics. These various currents, westward equatorial currents, poleward western boundary currents, eastward mid-latitude currents, and equatorward eastern boundary currents, form closed loops called subtropical gyres that dominate each ocean basin. The North Atlantic Gyre, North Pacific Gyre, South Atlantic Gyre, South Pacific Gyre, and Indian Ocean Gyre each circulate clockwise in the northern hemisphere due to the Coriolis effect, and counterclockwise in the southern hemisphere. At the center of these gyres, where currents circulate around a central region, water accumulates and becomes slightly elevated, creating gentle hills in the ocean surface, sometimes exceeding 6 feet in height, invisible to the casual observer, but measurable by satellite altimetry. These elevated centers also create regions of downwelling, where surface water sinks, carrying oxygen into deeper layers and creating the relatively nutrient-poor conditions that characterize the subtropical ocean centers. The Southern Ocean, unobstructed by continents, has a unique circulation pattern. The Antarctic Circumpolar Current flows continuously eastward around Antarctica, driven by the powerful westerly winds that blow unimpeded around the globe at these latitudes. This current connects the Atlantic, Pacific, and Indian Oceans, facilitating the exchange of water, heat, and dissolved substances between ocean basins, and playing a crucial role in global ocean circulation. Upwelling and downwelling, the vertical movement of ocean water, result from the interaction between wind-driven surface currents and coastal geometry or ocean basin configuration. When winds blow parallel to a coast, Ekman transport can push surface water away from shore. In the northern hemisphere, when winds blow with the coast on the left, in the southern hemisphere, with the coast on the right, causing deeper water to rise to replace it. This upwelling brings cold, nutrient-rich water from depth to the surface, creating some of the ocean's most productive ecosystems. The major upwelling regions off the coasts of Peru, California, Northwest and Southwest Africa, and in the Southern Ocean, support abundant marine life because upwelling delivers nutrients from deep water where decomposition has accumulated them back to the sunlit surface where photosynthesis can use them. These relatively small areas produce a disproportionate amount of the ocean's biological productivity, supporting major fisheries and dense populations of seabirds and marine mammals. As you rest peacefully tonight, imagine the vast surface gyres circulating in each ocean basin, driven by winds that blow with remarkable consistency across open water, deflected by the Coriolis effect into rotating patterns that have shaped ocean circulation for as long as continents have held their current configurations, carrying warm water poleward and cool water equatorward, distributing heat around the planet in ways that moderate climate and make Earth more uniformly habitable than it would be without ocean circulation. The deep, slow flow, thermohaline circulation. Descend now into the ocean depths, where cold, dense water flows along the bottom in currents that move slowly, but carry vast quantities of water throughout the global ocean, discovering the thermohaline circulation that connects surface and deep waters in a planetary cycle taking centuries to complete, regulated by temperature and salinity differences that create the density gradients driving this deep circulation. The thermohaline circulation begins in two primary locations where surface water becomes dense enough to sink to great depths: the North Atlantic near Greenland and Iceland, and the Southern Ocean around Antarctica. In these cold regions, several processes combine to create particularly dense water that sinks and flows along the ocean floor toward the equator and into other ocean basins. In the North Atlantic, warm, salty water carried northward by the Gulf Stream and North Atlantic Current releases heat to the atmosphere as it moves into high latitudes, cooling the water and making it denser. In winter, this already cool water is further chilled by cold Arctic air, and sea ice formation extracts fresh water as ice, leaving behind saltier and therefore denser water. When water becomes sufficiently dense, it sinks in regions like the Labrador Sea and the Norwegian Sea, forming North Atlantic deep water, NADW, that flows southward along the ocean floor. This sinking, called deep water formation or convection, transports oxygen-rich surface water to the deep ocean, supplying the oxygen that deep-sea organisms need to survive. Without this vertical circulation, the deep ocean would become depleted of oxygen, potentially creating widespread anoxic conditions, hostile to most marine life. The thermohaline circulation thus plays a crucial role in maintaining habitable deep ocean conditions. North Atlantic deep water flows southward along the western side of the Atlantic Ocean basin, following the contours of the continental slope and underwater ridges, eventually crossing the equator and continuing into the South Atlantic. This deep current moves slowly, typically just inches to a few feet per second, but transports enormous volumes of water, roughly 20 million cubic meters per second, equivalent to about 100 Amazon rivers. In the Southern Ocean, Antarctic bottom water AABW forms through similar processes. Cold surface water around Antarctica becomes even denser when sea ice formation increases salinity, creating the densest water in the world ocean. This extremely dense water sinks to the ocean floor and spreads northward into the Atlantic, Pacific, and Indian Ocean basins, flowing beneath the North Atlantic deep water as the lowest layer of the ocean's layered structure. The deep water formed in the North Atlantic and around Antarctica flows through the deep ocean for centuries, gradually mixing with surrounding water, slowly warming, and eventually rising back toward the surface in a process called upwelling that occurs gradually throughout most of the ocean, but more rapidly in specific regions like the Southern Ocean and areas of coastal upwelling. This return flow brings nutrients accumulated in deep water back to the surface, where they can support photosynthesis and biological productivity. The complete cycle of thermohaline circulation: surface water flowing toward high latitudes, sinking to form deep water, spreading throughout the deep ocean, gradually mixing and rising back to the surface, and returning as surface flow to high latitudes, takes roughly 1,000 years to complete. A water molecule that sinks in the North Atlantic today will not return to the surface until roughly the year 3000, having circulated through the deep ocean, mixing with waters from all ocean basins, and carrying dissolved substances and heat throughout the global ocean. This slow, deep circulation acts as a massive heat storage and transport system. The ocean holds much more heat than the atmosphere, roughly 1,000 times more in the upper ocean alone, and the thermohaline circulation redistributes this heat globally. Water that sinks in the North Atlantic carries with it the heat accumulated in tropical and subtropical regions, transporting thermal energy into the deep ocean, where it spreads globally before eventually returning to the surface and atmosphere centuries later. The thermohaline circulation also plays a crucial role in the global carbon cycle. When surface water sinks, it carries dissolved carbon dioxide into the deep ocean, removing it from the atmosphere and storing it in the deep ocean for centuries. This biological pump, the combination of biological activity that converts CO2 into organic matter and physical processes that transport carbon-rich water to depth, helps regulate atmospheric CO2 levels and influences global climate over long time scales. Climate change could potentially alter the thermohaline circulation by increasing freshwater input to the North Atlantic from melting Greenland ice and increased precipitation, making surface water less dense and potentially reducing or even shutting down North Atlantic deep water formation. Such a change would have profound impacts on global climate, potentially causing rapid regional cooling in Europe despite overall global warming, a scenario that has occurred during past climate transitions and remains a concern for future climate change. The thermohaline circulation connects all ocean basins in a global conveyor belt that unites the world ocean into a single interconnected system. Water that sinks in the North Atlantic eventually spreads into the Pacific and Indian Oceans. Water that upwells in the Pacific gradually makes its way back to the Atlantic to complete the cycle. This global connection means that changes in one ocean basin can affect circulation throughout the world ocean, demonstrating that Earth's oceans function as an integrated system rather than isolated water bodies. As you drift toward sleep tonight, imagine water slowly sinking in the cold North Atlantic, beginning a journey through the deep ocean that will last centuries, flowing along the ocean floor through underwater canyons and around seamounts, gradually mixing with surrounding water, carrying oxygen to the deep sea and storing carbon from the atmosphere, eventually rising back to the surface in the distant Pacific or Indian Ocean, warmed by the sun, and beginning the long surface journey back toward the North Atlantic to complete the cycle once more. The moon's tidal currents, lunar influence on ocean movement. Return now to the moon's influence on ocean movement, discovering how tidal forces create not just vertical rise and fall, but horizontal flows of water, tidal currents that can be powerful enough to generate electricity, that transport nutrients and organisms throughout coastal ecosystems, and that mix ocean water in ways crucial for global circulation and marine life. Tidal currents represent the horizontal movement of water associated with the vertical rise and fall of tides. As the tide rises in a bay, estuary, or coastal region, water must flow horizontally from the open ocean toward the coast to fill the basin, creating a flood current. As the tide falls, water flows back toward the ocean, creating an ebb current. These currents reverse direction roughly every 6 hours, following the semi-diurnal twice daily pattern of most tides. The strength of tidal currents varies dramatically with location, depending on the geometry of coastlines, the depth and width of channels, and the tidal range, the difference between high and low tide heights. In the open ocean, tidal currents are generally weak, perhaps a few inches per second. But in narrow straits, around headlands, and in funnel-shaped bays, tidal currents can reach several knots, nautical miles per hour, creating dangerous conditions for navigation and enormous potential for tidal energy generation. The Bay of Fundy, between Maine and Nova Scotia, experiences the world's highest tides, up to 50 feet of vertical range, and correspondingly, powerful tidal currents. Twice each day, billions of gallons of water rush in and out of the bay through relatively narrow channels, creating currents strong enough to be visible from shore, carrying nutrients that support abundant marine life, and representing an enormous renewable energy resource that engineers are beginning to harness through tidal turbines. Similar strong tidal currents occur in the Pentland Firth between Scotland and the Orkney Islands, the Strait of Messina between Sicily and mainland Italy, the Golden Gate entrance to San Francisco Bay, and numerous other locations where geographic constraints force large tidal exchanges through restricted passages. These areas have been known as hazards to navigation for centuries, but represent promising locations for tidal energy generation using underwater turbines similar to wind turbines. Tidal currents play crucial roles in coastal ecosystems by mixing water and transporting nutrients, larvae, and sediments. Many fish and invertebrate larvae time their release to coincide with specific tidal phases, allowing currents to transport them to favorable nursery habitats. Some species migrate vertically in the water column, in coordination with tidal currents, rising to be carried by surface currents during flood tides, and sinking during ebb tides to maintain position or move to new locations. The interaction between tidal currents and seafloor topography creates complex patterns of water movement and mixing. When tidal currents flow over shallow banks, ridges, or seamounts, they create turbulence that mixes surface and deep water, bringing nutrients from depth to the surface and supporting enhanced biological productivity. These tidal mixing fronts, boundaries between well-mixed water and stratified water, often support abundant populations of fish, seabirds, and marine mammals that congregate to feed on concentrated prey. Internal tides, underwater waves that propagate along density boundaries between water layers, form when tidal currents flow over underwater topography, particularly steep features like continental shelves and underwater ridges. These internal waves can have amplitudes exceeding 300 feet, though they occur below the surface and are invisible from above. Internal tides transport energy and mix water across vast ocean areas, playing a significant role in the global ocean energy budget and contributing to the mixing that maintains thermohaline circulation. The generation of internal tides represents a major pathway for tidal energy dissipation. Roughly half the energy in surface tides is dissipated through bottom friction in shallow seas, while much of the rest generates internal tides that eventually break and dissipate through mixing in the deep ocean. This tidal energy dissipation, ultimately derived from Earth's rotational energy through gravitational interaction with the Moon, amounts to roughly 3.7 terawatts globally, comparable to the total electricity generating capacity of the United States. Tidal mixing influences the distribution of heat, salt, nutrients, and dissolved gases throughout the ocean. In regions of strong tidal currents and significant seafloor topography, mixing can extend thousands of feet into the water column, affecting water properties and circulation patterns far from the immediate tidal currents. Computer models of ocean circulation must account for tidal mixing to accurately simulate observed water properties and circulation patterns. The moon's tidal forces also influence ocean circulation through their effects on the timing and magnitude of seasonal upwelling and downwelling. In some coastal regions, spring tides, the highest tides occurring at new and full moon, enhance upwelling by creating stronger tidal currents and more vigorous mixing, bringing nutrients to the surface and supporting pulses of biological productivity that propagate through food webs. These lunar influences on upwelling can affect fisheries productivity and ecosystem dynamics. Tidal currents can interact with wind-driven currents and thermohaline circulation in complex ways. In some locations, tidal and wind-driven currents reinforce each other, creating particularly strong flows. In other locations, they oppose each other, creating complex, time-varying current patterns. Understanding these interactions is crucial for navigation, for predicting the transport and dispersion of pollutants, and for understanding the movement of marine organisms that depend on currents for transport or feeding. The gradual slowing of Earth's rotation due to tidal friction, as tidal bulges in the ocean lag slightly behind the moon and exert a braking torque on Earth's rotation, means that tidal currents were stronger in the past and will be weaker in the future. 400 million years ago, Earth rotated faster, days were shorter, roughly 22 hours, tides were higher, and tidal currents were more vigorous. This gradual change in tidal forcing has influenced ocean circulation and marine ecosystems throughout Earth's history. As you rest peacefully tonight, tidal currents are flowing in coastal waters around the world, flooding into bays and estuaries as high tide approaches, ebbing back to sea as tide falls, carrying nutrients and organisms, mixing water vertically and horizontally, generating internal waves in the deep ocean, and demonstrating the moon's continuing influence on ocean circulation beyond the familiar twice-daily rise and fall of sea level that marks the most visible manifestation of lunar gravitational effects on Earth's oceans. Climate connection: how currents and moon shape weather. Discover now the profound connections between ocean currents, lunar influences, and global climate. How the transport of heat by currents moderates temperatures across continents. How tidal mixing affects ocean stratification and biological productivity that influences atmospheric carbon dioxide. And how the moon's stabilizing effect on Earth's rotation creates the predictable climate that has allowed complex life to flourish. Ocean currents transport approximately 25% of the heat that moves from tropical regions toward the poles. The atmosphere transports the rest, making them crucial for moderating global temperature differences and creating regional climates dramatically different from what would exist without ocean heat transport. Western Europe experiences mild winters despite lying at the same latitude as frigid Labrador, because the Gulf Stream and North Atlantic Current carry tropical warmth to high latitudes, releasing heat to the atmosphere that moderates European climate. The California Current, flowing southward along the western United States, carries cool water from higher latitudes toward the tropics, helping to create the mild summers characteristic of the Pacific coast. Cities like San Francisco experience remarkably even temperatures year-round, rarely exceeding 80 degrees Fahrenheit even in summer, because cool ocean water moderates air temperatures, with fog forming when warm air moves over the cool water and moisture condenses. El Niño and La Niña, opposite phases of irregular climate variability in the tropical Pacific, result from changes in ocean currents and wind patterns that alter the distribution of warm water across the Pacific Ocean. During El Niño, weakened trade winds allow warm water to spread eastward across the tropical Pacific, altering rainfall patterns, storm tracks, and temperatures across much of the globe. These events demonstrate how changes in ocean currents can affect weather and climate worldwide through teleconnections, correlations between climate conditions in distant regions linked by atmospheric and oceanic circulation. The thermohaline circulation influences climate over longer timescales through its effects on heat transport and carbon storage. Changes in this circulation during past ice ages and interglacial periods appear to have influenced the rate and magnitude of climate change, with reduced North Atlantic deep water formation potentially triggering rapid cooling events in the North Atlantic region. Understanding how modern climate change might affect thermohaline circulation remains an active area of research, with important implications for predicting future climate. Tidal mixing affects ocean stratification, the vertical layering of water by density, in ways that influence biological productivity and the ocean's role in the carbon cycle. Enhanced tidal mixing in some regions prevents strong stratification, allowing nutrients to reach the surface and supporting high biological productivity. The biological pump that removes carbon dioxide from the atmosphere through photosynthesis and exports organic matter to deep water depends partly on nutrients delivered by mixing processes, including tidal currents. The moon's gravitational effects on Earth extend beyond ocean tides and currents to influence Earth's rotational stability. The moon's presence stabilizes Earth's axial tilt at about 23.5 degrees, preventing the wild variations in tilt that would occur without a large moon. This stable tilt creates predictable seasons that have characterized Earth's climate for millions of years, allowing life to adapt to regular annual cycles rather than chaotic climate variations. Without the moon's stabilizing influence, Earth's axis might tilt anywhere from 0 to 85 degrees over periods of millions of years, creating extreme climate variations, ranging from ice ages when the axis is nearly perpendicular to the orbital plane, minimizing seasons, to periods of extreme seasonal variation when the axis tilts far from perpendicular. Mars, which lacks a large moon, experiences such variations in axial tilt, likely contributing to the dramatic climate changes that transformed it from a warmer, wetter world to the cold, dry planet we observe today. The moon also influences Earth's climate through its effect on day length. The gradual lengthening of the day due to tidal friction, roughly 2 milliseconds per century, has changed Earth's rotation rate significantly over geological time. Shorter days in the past meant different patterns of atmospheric circulation, solar heating, and Coriolis effects that influenced both atmospheric and oceanic circulation patterns, affecting climate in ways we're still working to understand through computer models and geological evidence. Seasonal variations in ocean currents, influenced by changing wind patterns and solar heating, affect regional climates in predictable ways. The summer monsoon in South Asia, for example, involves dramatic reversals in wind direction and ocean currents in the Indian Ocean, with currents flowing southwestward during winter and northeastward during summer. These seasonal circulation changes transport heat and moisture that create the wet summer and dry winter characteristic of monsoon climates, affecting billions of people. Ocean currents also influence the distribution of sea ice and the strength of ice albedo feedback, the process by which changes in ice cover affect how much sunlight Earth's surface absorbs or reflects. The Gulf Stream and North Atlantic current keep much of the North Atlantic ice free, even in winter, allowing the ocean to absorb solar radiation that would be reflected by ice, contributing to the relatively warm climate of the North Atlantic region and preventing the expansion of Arctic sea ice southward into temperate latitudes. Climate change is altering ocean circulation patterns in ways that will affect future climate. Warming surface water, increased freshwater input from melting ice, changing wind patterns, and altered thermohaline circulation all influence how much heat the ocean transports and where it releases this heat to the atmosphere. These changes will affect regional climates, weather patterns, marine ecosystems, and sea level in ways that scientists are working to predict and understand. As you drift towards sleep tonight, rest in appreciation of the complex connections between ocean currents, lunar influences, and the climate that makes Earth habitable. Currents transporting tropical warmth to high latitudes, tidal mixing affecting ocean productivity and carbon storage, the moon's stabilizing presence creating predictable seasons, and the entire system operating as an integrated climate machine that has maintained conditions favorable for life throughout the evolution of complex organisms, demonstrating that Earth's habitability depends on processes ranging from local tidal currents to global ocean circulation, to the gravitational dance between planet and moon that has shaped conditions on our world for over 4 billion years. The living ocean. How currents shape marine life. Rest now in contemplation of how ocean currents and tidal flows shape marine life, transporting larvae across ocean basins, creating nutrient-rich zones that support abundant ecosystems, influencing migration patterns of fish and marine mammals, and demonstrating that ocean circulation is not just a physical process, but a fundamental determinant of where and how life thrives in the sea. Ocean currents act as highways for dispersal, transporting the larvae and juvenile stages of many marine organisms across vast distances. Fish, crustaceans, mollusks, and numerous other groups release eggs or larvae into the water column, where currents carry them to new locations, sometimes thousands of miles from their birthplace. This pelagic larval stage allows even sessile adults, organisms like corals, barnacles, and oysters that remain in one place, to colonize new habitats and maintain genetic connections between distant populations. The Gulf Stream transports larvae from the Caribbean and Gulf of Mexico northward along the U.S. East Coast and across the Atlantic toward Europe. Some Caribbean fish species occasionally appear in waters off New England or even Europe, carried by the Gulf Stream during their larval stage, though most cannot survive in the cooler northern waters once they settle. This dispersal, while often unsuccessful for individuals, allows species to colonize new areas when conditions change, providing evolutionary advantages to species with good larval dispersal capabilities. Upwelling zones, where currents bring deep, nutrient-rich water to the surface, support some of the ocean's most productive ecosystems. The Peru current's upwelling along the South American coast creates one of the world's richest fishing grounds, supporting enormous populations of anchovies, sardines, and larger predators including tuna, seabirds, and marine mammals. These highly productive regions occur because upwelling delivers nutrients like nitrogen and phosphorus from deep water, where decomposition has concentrated them, fueling phytoplankton growth that supports entire food webs. The Antarctic Circumpolar Current, by connecting the Atlantic, Pacific, and Indian Oceans, facilitates the global distribution of many marine species. Some fish, squid, and plankton species have circumglobal distributions at southern ocean latitudes, able to migrate across ocean basins because no continental barriers obstruct movement. This connectivity affects biodiversity patterns, genetic structure of populations, and the ability of species to respond to environmental changes by shifting their ranges. Many marine species time their reproduction to align with favorable current conditions. Some fish spawn when currents will transport larvae toward nursery habitats with abundant food and protection from predators. Others spawn when tidal mixing is expected to bring nutrients to the surface, supporting the phytoplankton blooms that larval fish need for food. This coordination between biological timing and physical oceanography demonstrates the tight coupling between life and ocean circulation. Tidal currents create some of the ocean's most dynamic and productive habitats in coastal areas, estuaries, and around underwater features. Tidal mixing brings nutrients to the surface, supporting phytoplankton growth and creating feeding opportunities for fish, seabirds, and marine mammals that congregate at tidal fronts and areas of enhanced mixing. Some predatory fish position themselves in tidal currents to ambush prey being swept past, taking advantage of the concentration and transportation effects of strong flows. The lunar cycle influences not just tides, but biological rhythms in numerous marine organisms. Many species time spawning to specific moon phases, often releasing eggs during spring tides, when strong tidal currents will transport larvae over greater distances, or when mixing will be most vigorous, delivering nutrients that support larval feeding. Coral reefs, worm reefs, and many fish species show lunar periodicity in spawning, demonstrating that the moon's gravitational influence on ocean water also shapes the life cycles of marine organisms. Migration patterns of large marine animals often align with ocean currents. Sea turtles use the Gulf Stream to travel between feeding and nesting areas. Some sharks follow current boundaries, where prey concentrates. Whales migrate along paths where currents create favorable conditions for finding food, or where currents assist travel, reducing energy expenditure during journeys spanning thousands of miles between breeding and feeding grounds. The convergent zones where different currents meet often create productive feeding areas because they concentrate plankton and small fish at density fronts and temperature boundaries. These fronts are visible from satellites as sharp gradients in water color or temperature, and they attract fish, seabirds, and marine mammals that feed on the concentrated prey. Understanding current patterns helps predict where these productive zones will form, assisting both marine conservation and fisheries management. Changes in ocean currents can have dramatic effects on marine ecosystems. El Niño events, which alter current patterns and upwelling intensity in the Pacific, affect fish populations, seabird breeding success, and marine mammal survival across much of the global ocean. These events demonstrate how dependent marine life is on the physical oceanography that determines where nutrients are available and where productivity can support abundant food webs. Climate change is altering ocean currents in ways that will affect marine ecosystems. Changes in stratification may reduce nutrient supply to surface waters in some regions, potentially decreasing biological productivity. Shifts in current patterns may alter larval transport routes, affecting where organisms can successfully reproduce and maintain populations. Changes in upwelling intensity could affect the productivity of important fishing regions, with implications for both marine ecosystems and human communities that depend on ocean resources. The deep-sea ecosystems that depend on the slow rain of organic particles from surface waters are connected to surface productivity patterns shaped by currents. Where currents create high surface productivity through upwelling or mixing, more organic matter sinks to feed deep-sea communities. Where currents create nutrient-poor surface waters, less food reaches the deep ocean, and deep-sea communities are sparser. Even the deepest ocean life depends on circulation patterns operating thousands of feet above. As you drift peacefully into sleep tonight, imagine the countless marine organisms whose lives are shaped by ocean currents. Larvae drifting with the Gulf Stream, fish gathering at tidal fronts to feed, whales migrating along current boundaries, plankton blooming where upwelling delivers nutrients, coral reefs timing spawning to lunar cycles and tidal patterns, and deep-sea creatures depending on organic particles transported by currents connecting surface and abyss. The ocean is not a static environment, but a dynamic system where currents create the conditions that support life, transport organisms and nutrients, connect distant habitats, and demonstrate that understanding marine life requires understanding the physics and chemistry of water in motion, influenced by winds, temperature differences, salinity gradients, Earth's rotation, and the Moon's gravitational embrace that has shaped ocean circulation and the life it supports since water first accumulated on our planet billions of years ago. Sleep well, knowing that the oceans continue their eternal circulation. Surface waters flowing thousands of miles and wind-driven gyres. Deep waters creeping along the ocean floor in slow currents taking centuries to complete their journey. Tidal currents reversing direction every 6 hours in response to lunar gravity, all combining to create a system that distributes heat, nutrients, and life throughout the global ocean, moderating climate, supporting ecosystems, and demonstrating that Earth functions as an integrated system where moon, ocean, atmosphere, and life interact in ways that make our planet uniquely habitable in the solar system. Sweet dreams beneath the moon's gentle watch, where its gravitational pull creates tides that rise and fall with mathematical precision, generates currents that mix and transport ocean water, and helps maintain the stable rotation and seasons that allow life to thrive, reminding you that your existence depends on cosmic forces operating across scales from local tidal pools to global ocean circulation, from daily tidal cycles to centuries-long deep water journeys, all connected in a planetary system that has sustained life for billions of years and will continue long after tonight's tides have ebbed and flowed, carrying nutrients to coral reefs, transporting larvae to new homes, mixing warm and cold waters in the eternal dance between ocean and moon that makes Earth a living, breathing, beautifully dynamic world.